Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 72. In today's lesson, we are going to be continuing our work on red-black trees, and we will be adding search and delete. So last time we added insert, so now we're going to do search and delete. So let's begin here. So we have a little program already set up to be able to test this. So we'll just go ahead and get started. So the first thing I'm going to do is going to add a helper method. So let's add a private, and it's going to return a red-black node. So those are the nodes that we've created for our red-black tree, and it's a nullable node. Find node. The reason I'm going to create this helper is I'm going to use it in both search and delete. So we're going to have our current equals root. So we'll start at the root. And now while current, I'd rather use is not null. There we go. All right. So while it's not null, let's do value. If value equals current.value, return current. So if the values are equal, we found it. Just needs to be inside the loop. So otherwise we need to update current to equal value less than current.value. So if it's less than the current.value, it's to the left. So then we can do current.left, else current.right. And return null if we don't find it. And that should be our find node. And that pretty much finishes search. So we'll add a console.writeline here. Let's see, we'll do a new line, search, value, close. The dollar's in the wrong spot. There. So we'll do that, and finally we will return find node, value is not null. So if the node's not, so if we find the null or the node, it's there, we return true, else we return false. And this should be bool. No, it should be red, black node. There. Wait a minute. Let's open up AVL tree for a second. What did I do for search here? Bool. Okay, so we return bool. So yeah, let's go that route because that's the way I intended it. Bool, so it's there. We'll do it like that. I must have copied the wrong one before. But that's the entire search. So just this. So this is slightly different from what we did in the BST, but this is basically the same for functionality. So the difference here, for search over here, we did a separate search method, but all it does is it here, if the value's the node, we found the value, we return true. Else, we check the value, current in my case, and then we search for the left and we search to right. So this one does it recursively. This does it iteratively. So these are doing basically the same thing, and I do a little bit of more work here. Maybe I should check null if it's null ahead going in, but I'm actually not checking for the node. I'm checking for the value. So it should be fine. So this one's a recursive. This one's not a recursive. So as you see, there's not a lot of difference. This one's usually a little more straightforward, but you could interchange either one of these. I'm doing it this way, because it was different. Oh, and I've split it out because we're going to need it here for delete. So that's the search though, and that was very quick. So delete is not going to be very quick. This one is involved. So there's a couple cases. So first thing, let's add some more helpers. So I'm going to add a private static red black node minimum. So this is looking for the smallest. So while node left is not null, node equals node.left, and return node. So we'll see how we use that one in a minute, but basically we're just looking for the smallest node in the tree. So now let's do another method. So this one we're going to call transplant. So this one's the one that's actually going to do the movement. So it's going to put the node wherever it belongs in the tree, and we'll use it in a couple spots. So we'll have a private void transplant red black node. We'll do target red black node replacement, like that. All right. So if target.parent is null, so if the parent's null, then root equals replacement. Let's do else if target equals target dot parent dot left. So if their target's the parent's left child, then target dot parent dot left equals replacement. Now this is going to be the other case. So target dot parent dot right equals replacement. Forgot an equal sign there. Else, so else we would set the parent to the target, or the replacement's parent to the target's parent. There's a little case here though, if it's null though, so we'll do replacement. And if it's null, if it's not null, we'll set it like this. So by the way, I don't know if I've actually touched on doing this like this. What this is a I think it's still null coalescent, but basically it's letting me conditionally assign. It's saying if replacement isn't null, set the parent. So it's equivalent to let's see. Here, let's see if it'll just do what it's equivalent to. No, I think it'll be the same thing as if replacement is not null, target or replacement dot parent equals target dot parent. Well, I think it's equivalent to that, and in fact, I bet this is what this tells you. Use null propagation. Yeah. So basically, we're just checking that the replacement's null or not, and if not, we don't set it. That's a newer feature, apparently, though. I think that was actually introduced here in .NET 10, so this may not be available if you're still on .NET 8. And in that case, you have to do the full if block. All right. So there's us two helpers. We'll actually have one more helper, but you'll see why we're not going to do it separately just yet. So let's begin. So delete. So let's do a console.writeLine. And this will be the same as before, /n, delete value. Tell us what we're doing. And now we begin. For node equals find node. So we want to find the value. So we find that value. If the node is null, that means we didn't find the value, and we can just return. So otherwise, so if we don't find the value, there's nothing to delete, and we're good. So now not found. We found. We are done with delete. All right. So first thing we want to do, and I'm going to use the terminology you'll probably see if you have the textbooks on this or anything, you'll probably start seeing these more like this. Y equals node. So Y we're going to use as one of the two values for replacement. The other one's going to be X, and we'll have to keep track of those, and we'll keep track of the color. So here we'll have var Y original color equals Y dot color. So there's this error. We get the original color. Now we'll need a red black node X and a red black node X parent. So these are set up for what we're going to need to do. So to begin, if node.left is null, so if there's no left child, we're good here. So then we can just do X equals node.right, X parent equals node.parent, and transplant node right. So there we just use our transplant method and just swap the right child with node, and we're done. Or we'll have a else at the very end. We'll do the cleanup. So if Y original color equals node.black, node color dot black. No, it should have been the other way. Node there. So if that's the case, then we'll have some work to do here. So fix the deletion. But otherwise, we will be done in this case. So here, one child to the right. Easy case. All right. Now we'll do the other one. Here, and let's move this. We'll move that there. Now let's add an else if node.right is null, x.node, x equals node.left, x parent equals left, node.parent, and transplant node right. Now you see why, wait a minute, that should be node left. Now you see why we did the transplant method. So each one of these would have the same logic. So pulling it out, we're just able to reuse it here. That's good because we're going to see it again. This one's the one child to the left. Easy case. Both of those, not too bad. Now what happens on the other side though? So here, else, two children. Hard case. All right. So this one took me a little bit to get right, so hopefully we can get it right today. So Y equals minimum, so we need to find the smallest. Node to the right. Y original color equals Y dot color. And X equals Y dot right. So here we've reset all of our starting values. So if Y dot parent equals node, so if the parent's the node we're looking for, so X parent equals Y. So here I wrote a comment here. So X parent should be Y even if X is null. Keep track for fix up. So that's something we're going to need in the future. And you'll see why when we do this fix the deletion, we'll show this again, but I wrote this here to keep track of that. So here, in this case, what we'll need to do is we'll need to do some transplanting. So the transplant here, what we're going to do here is we found the minimum node, we got its color, we set the right side to be X. So now we're going to handle Y. So we're going to be transplanting it and the value that's X. And we'll do some fix up after that. So we'll do transplant Y and then Y dot right. Now we'll do X parent equals Y dot parent. Y dot right equals node dot right. And Y dot right. And we'll do this, the null coalescing again. Parent equals Y. So there, that's just an indication that Y right here can be null. So there handles this, the case where the parent node was null. Finally, now we need to actually do the cleanup. So now we'll do transplant node Y dot left equals node dot left, and Y dot left parent. So we're doing the null coalescing again. Y dot color equals node dot color. All right. So that pretty much gets this method. There's something wrong though, so let's run it here with the fixed deletion here missing. Let's see what happens. So let's do we'll just make this tree for now. So we'll do we'll add 11, add 20, add 6, add 7, add 3, add 4. So now we've got this tree. Now let's delete 6. So now I'm trying to remember what our 3 rules were now. Let me see. I wrote them down in my notes. 1 second. So the rules, root's black, so we're still good there. And you can't have 2 reds together. We're still good there. Let's see, what was the other rules? All null leaves are black. Red nodes cannot have red children. We're still good there. And every string contains the same number of black nodes. So I think we're actually balanced here. So maybe delete doesn't need fixed up in this case. Maybe that actually worked all right. Let's add a 5. Yeah, let's add a 5. There we had to do a little bit of rebalancing. Let's add a 6. And there it did a lot of rebalancing. Okay, now let's delete. We'll just delete 7. Oops. I think that actually stayed balanced. So I may not know how to show the case, but case. Let's try to make. Let's see. Delete 4. Does that fix it? There, red child. There we go. that's what I was trying to get, was some case that was invalid. And it's like, I thought the original removing the 6 here would have done that, but I guess I'd have to do the math, or do the follow it through. But I think that's right. This one is invalid though, because there's a red with a red child. So that's what the fix up's going to do, is actually fix those cases. And I think it was rule 4 and 5, the number of black nodes on the path have to be the same. I think those were the two that this case really works on. I'm surprised it was that hard to get the case though, so that's a good sign. So we may have insert working pretty good. But now we need to actually handle the deletion. So let's call this fix deletion. There we go. And we'll pass in, I think I just want to pass in X and parent X. Yeah. All right. So private void fix deletion, red black node. What did I call this in my test? Okay, I stuck with the name X and red black node parent. All right, so let's see what happens here. So parent is the parent of X when X may be null. So even if an X is null, it's still a parent. So here, this is going to be a little more complex while condition, but we can work with it. So X does not equal the root. So X is not the root. And X is null, or X.color equals black, right? Black. Yeah, node color black. So this will get the case. So it's not the root. If it's the root, we're done. If it's if X is null or it's black, then we do some work here. So here, if parent is null, we're done. Easy enough. Let's Copilot one there. If parent dot left equals X, so if the left child's X, then var W, so this will be another value, so equals parent, it's not parent dot left, it's parent dot right, the opposite side of the one we're working on. Now we need to check the sibling. Sibling red. So if W is not null, so make sure it's not null, and the color is red. So if the color is red, then we'll do the updates. So we'll make the color black. Yeah, Copilot doesn't know what we're doing apparently. Node color dot red. Rotate left. So that's using the rotate left we wrote last time for the insert, by the way. W equals parent dot right. All right, so that handles the red. So now our sibling node that we're looking at is black. So now we need to fix up the counts. So if W dot left is null, or W dot left dot color equals node color dot black, and w dot right is null, or w dot right dot color equals black. Should be just figure out if I got the parentheses wrong. This one shouldn't have closed. There. Okay. So this case, so if W or left is null, or the left color is black, or right is null and black. So that's taking advantage of the rule that a null node's always black. So both of these are black cases. So we'll do W dot color, null coalescent again, node color dot red, x equals parent, parent equals x dot parent. All right. So if this isn't the case, what it is. So else, now if it's not the case and it's red, then we've just made the parent red. Now this one's red as well, right? And now if we rotated red, I guess. No, I guess the parent would be black. We made W black. We rotated the parent. Yeah, so it's got to be siblings red, and but maybe this is the more common case. Let's see. So if W dot right is null, or W dot right dot color equals node color dot black. All right, W dot null coalescent again, color equals node color dot black. So this one would have a double if statement there. Color red. And if W is not null, rotate right. So this is a LR rotation, or sort of. Parent dot right. All right, I think that's this case. If W is not null, W dot color equals parent dot color. Parent dot color equals node color black. W dot right dot color equals black again. Right. Yeah, right. Rotate left. Parent. All right. So now x equals the root. So that's the one we're removing. Parent equals x parent if it exists. So this is another else. So this else goes all the way back up to if parent left is equal to x. So else x is parent's right child. All right, so this one's going to be very similar, but basically inverted. So here we grabbed right and went that way. Here we're going to grab left. If W is not null and W.color equals node color.red, black, parent.color equals red, rotate, we did left before, so this one's a right, parent dot left, I think, left, let's see, yes, okay, so I think this is right track. So if two of them dot right is null, or W dot right dot color equals node color black. So this is just that same check again, making sure it's null or black. Equals node color dot black. Did I make the same mistake again? Oh, I didn't start it this time. There. Technically, I don't think the outer ones are required, or this one and this one and this one and this one are required, because I think and got precedence here, but I don't want to try to remember that for sure, so I'm just going to add parentheses. I think that's the case, though. W.color equals red. See red. X equals parent. Parent equals x dot parent. Else. So here's the else condition. So this is the double we had before. So if W dot null coalescent left is null, or W dot left dot color equals NCB, W null coalescent right, this was the big one, color equals NCB or if W is not null, rotate left W not X. Wait a minute, that was about to be a mistake. W equals parent dot left, and I'm hoping I've got this right. If W is not null, W dot color equals parent dot color. Parent dot color equals NCB WL, no, W dot left dot color equals NCB rotate right parent. The NCBs, by the way, are just node color black. If you use your IntelliSense, it's trying to take the first letters of stuff a lot of times. I'm trying to use it a little more. All right. So then we have one final step. 1, 2, 3. Here, x.color equals NCB. So at the very end, we set node color to black. And I think this will have us working. So let's see if we can create a situation where we see that previous case. There. All right, insert. Oops. 11, 20, 6, 7, 3, 4. See, we deleted 6. What did we do then? We delete 4 then. And then we added a 6, added a 5, added a 4, added an 8, added a 9, added a 10. All right, so let's do some deletions here and let's see if we can break it. So right now, everything looks pretty balanced actually. So let's remove the root. Oops. That was not intentional. Here, let's just try to get something similar. We'll do 11, 20, 7, 8, 6, 9, 10, 5, 4, 5, 3, 2, 1. Now, no, not 6. We'll remove 7. All right, the properties stay the same. I think so. So there's no 2 reds. So to get to a so from here there's 3 blacks. Get from here there's 3 blacks. Get from here there's 3. Get from here there's 3. Get from here there's 3. Yeah, I think that's still good. So let's remove 4. See what happens there. So that time we remove this one, and these rotated. So now 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Still seems good. There's only 1 red each time. Let's remove one with 2 blacks if we can. Let's remove 8. Right, so 9 went up. These got rotated a little bit. So let's see. 3, 3, 3, 3, and 3. Okay. Let's remove the only red. So remove a 2. Changed it quite a bit, it looks like. So let's see. So 3, 3, 3, 3. Yeah, I think it's working. I think it's keeping the properties now. That's a good sign. So let's remove one more. Let's remove 11 over there. Now, 1, 2, 1, 2, 1, 2, 1, 2. Yeah, I believe it's keeping us pretty balanced. So in some of these cases, the search could be a little bigger. So like right there, that search to get to 1 here is going to be a slightly bigger than anywhere else in the tree, but it's not majorly larger. And that's what red-black tree is doing. So it's doing a little more loosely on the search, or a little more loosely on search, and in doing so, it doesn't have to do less work. And it feels like there was probably more work, but if you look in here, this is an if condition. There's a while here, so we are having to loop through, but there's a lot of if happening here. We're not looping multiple times or anything. We're just looping through once. And we're always picking, let's see, it's X. So where do we set X? Right there. Do we set X anywhere else? There. And there. So for the most part, we're not going to be doing that many operations. We're only going to go through this loop a couple times, hopefully, but that's the goal here in working with trees. We're not looping through the entire data structure. We're only going through the parts we need to go through. So that's been red-black trees. I actually don't know what I'm going to move to next. I'll have to think on that just a little bit, but this has been trees. These are the 3 most common trees I see in literature. Red black tree is actually the only one I think of actually ran into before. So take that for what you will. I guess file systems feel like a tree, so maybe they're implemented as one of the others, but the only one that I could tell and knew which one it was is a red black tree. So we'll call it there. Actually, a little short. I was expecting this to go longer, but once you sort of got into the flow on the fix up here, because like the two sides are identical to each other, it's just everything's flipped. So all the logic here is doing is maintaining those three there's 5 rules. The root being black's easy, and each node having to have a color is easy. So the 3 rules here are the ones that are being upheld by this code. So yeah, we'll call it there. This has been Programming with Shadow, episode number 74. Thanks for watching, and have a wonderful rest of your day.